Good morning, everyone. Thank you for joining our webinar today. My name is Chris. I am the marketing account for Rotoglass here in North America, covering the United States and Canada. Today, we have a very special webinar presentation for you with a guest speaker. We're covering in the investigation of timber concrete composite floor systems in mass timber. And if you do have any questions at all, we will look to answer those towards the end. The Q&A section on a computer is in the top bar. You can click that, send your questions in there. Or if you're on a phone, there's three dots at the bottom right hand of your screen that'll also open up the menu and allow you to navigate the Q&A section. So without further ado, I'm going to pass the microphone on over to Gloria. All you.
Okay, good. Well, thanks so much. Good morning, everybody. Thanks so much, Chris, for the introduction. My name is Purya Bahmani, Assistant Professor of Structural Engineering at Washington State University. Quick introduction, and I will go through the presentation that I have. My background is structural engineering and also earthquake engineering. Received my PhD degree from Colorado State University in 2015. Involved in the NESOF project. I was the lead PhD student on that. It was in 2013, a shake table test. After that, I worked for about 5 years in industry at KPFF and MKA in Seattle and Tacoma area. And then after that, I joined academia and Milwaukee School of Engineering for 3 years. And then in August 2022, I joined Washington State University. My field of work and research is earthquake engineering and also the mass timber and hybrid structures. So this presentation or webinar is all about hybrid system and how we can use mass timber plus concrete to make a very efficient hybrid system, and in this case, floor systems. Just a quick note on this. This is part of my master student, Munder Naife. He graduated this summer. He went to TY Lane in Sacramento in California as a structural engineer. So most of the work has been done by him, testing and basically the construction. So I just want to give the credit to him as well. Quick overview of timber concrete floor system. So it's like, from World War I and World War II, they developed this system of using concrete and CLT. Well, not CLT on that point, it was basically just heavy timber to be able to increase the capacity of the structure. In 1922, nails and steel brace as shear connections. Then in 1956, gamma method was developed, which was really good on that time, still being used, but that's only we will go through that. That's only for positive moment with a lot of limitation and assumptions. And then in 1990, we've got the Eurocode and bridges that they started to use the timber and concrete. Then around 2000, elasto-plastic method, which is the strength method that we actually use to verify our experiment or validate the elasto-plastic for negative moment, has been established. And then in 2017, and now it's 2025. So it's basically a history of that and how we can use this composite system. So a little bit of overview of the different ways of transferring moment in a floor system. So what we have is a simply supported structure, which is on the left, as you can see. Let me see if I can put that one over here, laser pointer. So this is the simply supported beam. What you can see is with the just uniform load on top of it, you have the shear diagram and then the moment diagram. As you can see, it's always a moment, positive moment. What is positive moment? Our convention in the US is the compression at the top, tension at the bottom fibers. We call this positive moment. And negative moment is when tension is at the top and compression at the bottom fibers. When we have a multi-span or continuous support, continuous span. What we have is negative moment is going to be developed at the support. So in other words, you have positive moment and you have negative moment. What is really important over here is you can, if we go continuous span and if we can develop negative moment and resist negative moment at the support, we can increase the or you can increase the capacity, or in other words, we can decrease the demand from the positive moment. The positive moment will reduce to here, and then some part of that is going to be shed to the support as a negative moment. So what is really important over here is our research is like working on a timber concrete, but not just for positive moment, for simple support. We would like to develop that and validate it for negative moment, so we can use it for continuous span. And if you can do that, it's going to be a lot more efficient. You have basically less demand, and you can go for longer spans for like office buildings, hotels, when you have when you don't want to like see a lot of columns in architectural parts. So very quick case study. If we put this in like SAP 2000, very simple structure. If you have like simply supported beam and then you've got a multi-span, we have like trials because when you have a composite system, which I will go through the definition of that, depends on where you have positive or negative moment. The flexural stiffness, which is EI in a structural engineering, we use like EI for like flexural stiffness, that is going to change. And then you need to find like a way of finding the the try and error to be able to find how much of that beam is going to be on negative moment and how much in positive moment. So let's go through this very quick. So I have a continuous span at the top with 50 live load and like dead load of 61 PLF over here. And then what I have is a simply supported right over here with the same dead load and live load. What you see right here is a moment diagram, as this is the negative moment, this is the positive moment, and the same load, the same span. If I don't want to have the continuous, then what I have is a positive moment that goes higher. So in other words, if the capacity is like if the capacity is 13,939 or 13,390 pound-feet, and then in that case, for the continuous span, this beam is going to be safe. But for positive or simple supported span, this is not going to be safe because the demand is higher than the capacity. So the other thing that's really important is hybrid systems and hybrid structures. So if we can use the materials where they perform the best, we can optimize the performance of the structure. So that is a like general statement. That's why we have reinforced concrete. So concrete is really good in compression, then not really good in tension. So we add rebar such that it can like reinforce it for tension or tensile stress. So the same thing that can be applied to any other like hybrid system. So in this case, timber and concrete. So how we can combine them together and use it very, very efficiently. So let's go through composite action and definition of that, because that's the like base for this webinar and presentation. So what I have over here is a composite action. At the top, you have no composite action. And then what you have is layer 1 and layer 2. You can say like concrete at the top, CLT at the bottom, but it's a very general system. And in this case, if you apply a positive moment, let's just think about positive moment, you have two layers and they do not talk to each other. So there is no shear transfer between these two layers. So what you have is you have neutral axis for the first layer, and you have neutral axis for the second layer. You have M1 and M2, and then M1 plus M2 would be the capacity of this section. Now, if you go to the right, and it's a composite action, you have two layers, the same layers, but then you can add, somehow you can add a connection between these two layers, which we will talk about. such that they can transfer shear and then basically they can talk to each other. So if that is the case, you have M1, I call it M1 prime because it's not going to be the same as M1 over here, and then M2, but then you're going to have only one neutral axis. And then the shear right over here is going to add axial load over here at top and at bottom, which is basically these two axial loads. So as you can see, these two axial loads are going to be exactly the same. You can call it T for tension and C for compression. And then these two make a couple. And as you can see, there's a force, there's a distance between them, and you can add a moment over here. So that is why composite action is going to be more efficient, because you have two small m's, but then the big M over here is going to help increase the strength of that structure. And then the challenge is how you can connect these two together. So that is the challenge. That's how we will like to address that in the TCC or timber concrete composite systems. So what I have over here is a positive moment compression top, tension at the bottom. What you see is concrete over here and CLT over here. And then there will be a slip right there. So if it's 100% composite action, there shouldn't be any slip. If it's basically zero composite action, you will see a lot of slippage in between them. And then if it's intermediate, so not like 100% or like not zero, then you will see a little bit of slippage, but also a little bit of shear transfer. And that's what a structural engineer can play with to transfer the shear between these two layers and increase the capacity based on what kind of shear connection he or she is going to use. The same thing is going to happen for the negative moment, but then which is the part for this webinar. So the negative moment, the problem is concrete is not good in tension. It's going to crack really easily. So you need to add reinforcement to transfer the tension. So as you can see in this stress profile, we only have one load for the rebar over here. This is the spring, so like the virtual spring that we put there to model the shear connections between concrete and CLT, and then there will be the stress distribution over the CLT. It would be really hard to get 100% composite action, so we usually have like 70%, 80% composite action in these systems. For the timber concrete composite floor system, particular for that, what we can have, it's not just for CLT, you can have glulam or other mass timber members at the bottom, and then a concrete at the top, concrete slab at the top. If it's for only positive moment, the concrete slab is not going to have any reinforcement except like temperature and shrinkage. It still needs the dowels basically to transfer the shear, but I was trying to like say there's no like rebar or very minimum amount of rebar. If it's in negative moment, then you need to add the rebar, and those are the structural component of that system. As far as the connections, now, if I want to just think about the connections, now what we can have dowel type fasteners, which is the focus of this webinar. You can have notch connection. So in other words, we like make a notch in CLT, basically instead of the screws, you have a notch, and then it's all based on the bearing capacity, and the concrete bears on the CLT, and based on that, you can transfer the shear. You have longitudinal connections, and you can have adhesive or glued connectors. For this webinar, we are going to focus on screw or dowel type fasteners. And then based on it's going to be like based on many tests. So in other words, either you have that screw and you know what's going to be the capacity, strength, and also stiffness of that, or it has to be tested. So what we use, Rotoblas provided those tests. That's from like the ETA in the Eurocode. Provided a test. It's a monotonic test with loading, unloading and like full load to the full capacity. And based on that, you can find the force P, and then the delta over here, the displacement. And based on that, you have the force displacement, you can get the stiffness and also strength. Two different tests that can be done. Both of them are like valid. One is a symmetric shear test that you put the CLT here, two concrete, and then screws. And in this case, it's a double shear. So P divided by 2 is going to be resisted by 1 screw, and then the delta. So that gives you the stiffness. In this case, you have a rollover here, and then only 1 screw. So in this case, it's P divided by delta. A little bit background on the gamma method. So I'm not going to go through the detail of this. It's kind of beyond the scope of the webinar to go through all the equations and like the differential equation, but just to let you know that it's there is a base for the gamma method and how we deal with the how we can apply that to the timber concrete composite floor systems. So this is the Euler-Bernoulli equation for beams. So it's a differential equation that like one side of that has like the flexural capacity, and it's all about the beam capacity and behavior. And on the other side of that is the load. So Qx or like omega x, Wx, depends on what textbook or what code you use, those notation will change. But that is like based on plane section remain planed, no slippage between the layers, and no shear deformation. And in other words, like no contribution of shear for the deflection or finding the displacement of that beam. In the TCC, what we have is there will be some slippage between concrete and CLT. And we also have shear deformation because these are like thick, and also a shear is going to like have more contribution. So we cannot just ignore shear in this case. So the gamma method, basically the one that has been used for, I don't know, like 30, 40 years or so. So the gamma method is basically based on a few other assumptions too. So it's Euler-Bernoulli, but also it's based on sinusoidal load applied to that. So Qx is going to be something like sine or cosine, as I show over here. And then what we have is we've got like deflection on that and the curvature. And then based on that and based on the boundary conditions, you can go back and back calculate these constants. So in other words, there's a differential equation. We have the load. Now we are going to go back and back calculate the C1 and C2, which are the constant of that differential equation. And in this case, you have an equation that gives you the capacity of a timber concrete composite floor system, but for this load and also simply supported. So everything is about positive moment in this case. What you see over here is, if I want to explain this one over here, it's concrete at the top, CLT at the bottom. You have that's a cross section of TCC. And then, as I mentioned, what you have is MC, which was like M1, like layer 1. So that's M for concrete, that's M for the CLT. But also what we have is, due to this spring or those connections, you can transfer shear. So if you have shear, then if you cut right over here, that like when you add or sum all the shear stresses, it's going to be the same as NC, or the axial load in concrete and axial load in CLT. Now, these two is going to give you that couple, which gives you the advantage of having a composite action versus not having a composite action. And that part is basically right over here. So that's the N that you can use, and then multiply that by the R, and R is the distance between NC and NT here. So I'm not going to go through the detail of this. As I mentioned, we don't have time for it. But if you go through equations, still in gamma method, we have positive moment, we have negative moment. So you will have two different flexural capacity, because this is an unsymmetric shape when you look at the structure. So concrete at the top and CLT at the bottom. So either like, if the CLT is mostly in tension, concrete mostly in compression, you have different behavior and different flexural capacity than when you have concrete at the top and it's in tension, and CLT at the bottom and it's in compression. So you have a different for negative moment. So you have different EI effective, and that's why you need to do some trial error to be able to find the exact capacity based on the load and the span for a continuous span. Now, what we have over here is another way to do the design is the ultimate limit state design. So in other words, like how we can just, instead of going through the gamma method and based on that finding the capacity, we go through the capacities of the section top and bottom, how much concrete can take, how much CLT or the timber part can take, and then also how much of that force can be transferred through shear, the dowels in this case, or the screws. And then based on that, we have two limits. So one is brittle, like the connection are going to be brittle or not allowed to yield. And in this case, you can use the gamma method in this case. And then, but the connections are going to be really stiff and strong. So in other words, they should not yield at this point. The other way is we have a ductile system. It's like elasto-plastic or EP method that is based on the forces inside of all the components, and then it is assumed that the connection is going to yield or really close to the yield capacity of those connections. And then what we have is timber, plastic connections, and concrete. Then we get a timber concrete composite floor system. So now, what we have over here for negative moment, because everything has been done in positive moment, so we are not going to like talk about positive. It's been established, tested, so we know how to design those things. But for negative moment, when we have a continuous support, then we have two equations. So and minimum of those two capacities are going to give us the capacity for the TCC when it's subjected to negative moment. One is basically based on this, which is the first method that we have, like the gamma method, and like how much capacity we can get. And the other one is going to be the elasto-plastic. So if it's elasto-plastic and everything is going to yield, then what would be the moment? The minimum of those two is going to be the strength of that TCC member. Over here on the bottom right, what you see is a force displacement. It's a really qualitative way of showing what is happening, and we will see that the test data and how this is really close to what we tested. So when you test a TCC member, if it's no composite action, you are going to be like somewhere over here. If it's full composite action, you're going to be somewhere over here with the initial stiffness. If it's between, then we will have a red line over here. That gamma method can predict the capacity, or sorry, the stiffness for before things go to the yielding and like full capacity of the structure. But after that, you have some yielding and like some partial failure in in concrete or in steel. Or CLT, and then we have a bilinear action. At one point, elasto-plastic method is going to be very good to predict the capacity. So what we did, we wanted to use the elasto-plastic method, which is established, but we did some adjustments. So we added like a few notations and add a few more things to that equation, basically, to be able to use it for negative moment. So what we have is, and we've got a CLT at the bottom, concrete at tops, and TCC floor structure. It's about like 20 feet long from here to here, and then we push it from one side, and we wanted to do that because we wanted to have the entire slab to see negative moment. So I did not want to have positive moment and negative moment, because now in that case you have like try and error to be able to find what is EI effective, positive, and negative. We just want to focus on negative moment. In this case, we used Rothablas CTC 9160 screws, and those are basically the screws that can be driven to CLT at 45 degree, I believe on 30 degree as well. So we use pairs of 45 degree, as you can see right over here. And then that's my student Munder that, about like 6 or 7 months ago, he was like working on this project and put everything together. And then we also had the reinforcement. So that's a reinforcement, the longitudinal reinforcement that we used for our calculation. We also had these small reinforcement at, I believe, 12-inch on center. That is the for just temperature and shrinkage. This is like transverse reinforcement in this case. So for the test, what we have, and that is true for any experimental test, we need to test all the components. So we cannot just say, well, this is based on nominal capacity or this is based on a catalog that we can use. So because when you test things, there is no safety factors, there is no like statistics that you use like 5 percentile of the capacity of lumber or so. We need the expected values to be able to use them and then put it in the analytical work and then verify it by an experiment. So what we did, we test the CLTs in shear and in flexure. We test the rebars and we also test the concrete to be able to then put those capacities to the analytical model, which was a gamma method and elasto-plastic method. And at the end, we did the test and then verify that this is like, the elasto-plastic method was working, or we need to have some adjustment basically. So this part is like, this slide shows all the tests that we did at Washington State University. That is CLT shear test based on ASTM D198 or PRG 320 for like CLT. If like you're familiar with CLT and guidelines in the US, we use PRG 320. And when we tested, so we tested 10 5-ply SPF number two CLTs. And then in this case, you can just go back and calculate the GA and the effective shear stiffness. So this is the force displacement based on this. You can go back and back calculate the GA for the CLT. So we have again, this is the shear test. You can see the rolling shears, and that's when we have failure. So this is good to know what kind of failure you have. But again, we did this because we wanted to have the parameters to be used for the TCC tests. This is the bending test or flexural test, again, based on ASTM D198 or PRG 320. We tested 6 5-ply CLTs, and those are 12-inch wide, but 178 inch long, because we have to have a good length to depth aspect ratio for these tests. 2-point load, as you can see, that's an actuator, 2-point load coming in. And then in this case, we can have the mid-span deflection versus total applied load. And based on this, you can find the EI effective for CLT. And it's a symmetric structure, so it's EI effective for only CLT is going to be the same for positive and negative moment. This is after these tests, we that's a failure. You can see a rolling shear, a tensile failure at the bottom, and then you can have finger joint failure at the top. I would say most of the time, since the tensile capacity of lumber is going to be less than the compression capacity, when you're testing CLT for flexure, the tensile at the bottom, because that's the fiber that sees the most tension force, it's going to fail. And as soon as you have this failure, it's going to progress to the top. So it's going to be a really sudden failure. So if I go back to this slide, to the previous slide, as you can see, one failure is going to make the drop. So 1 or 2 cracks and then all the way down. So there is no ductility to the system. And we also tested the rebar. So we used grade 60 rebars for the longitudinal, and then grade 40 for the transfer. So for the calculation, we use grade 60 for these tests. And at the end, we did testing. So at the time of testing the TCC floors, right at the same time, we tested the concretes, and that's basically, we had a few tests to make sure that, we get to the point that 4 KSI concrete that we wanted to have for the design. And then that's 4,000 PSI or 4 KSI. And then this is like the time that we did the test. So test 1, 2, and 3, and 4, very, very, very close to what we had. So we were right on the concrete capacity that we were looking for. And that's for this, the modular rupture for concrete. We also tested this because in this case, we have tensioning concrete. Although it's not really important for design and we neglect it, we wanted to have that to make sure that we don't miss anything as far as the capacity and validation. Now, if you go to the experimental test for the TCC, we had 4 specimens. We designed all of them the same way. And because we wanted to test multiple times, making sure that we have good statistical and data. With on one test, you cannot just have a good data. What we did, we had the small specimen that is about 20-inch wide, and then the rest was about 39 or 40-inch wide. We had CTC screws from Rotherblot at 8-inch on center, and those were double or pairs at 45 degree. We had 10 and number 5 rebar for longitudinal, and then the transfer rebar that we used was the number 3 transfer rebar at 12-inch on center. This is the profile of the section line longitudinal, and that's a cross section for a small specimen and also the larger specimens. And we made it such that it does not have any conflict with the screws, like the reinforcement and the screws. For the test setup, as you know, we need to add a lot of instrumentation because it's not just about load and displacement. You need to know, for example, what would be the strain condition and status at these rebars. So inside of all the rebars, on top part of the rebar, we add the strain gauges. We protect it when we pour concrete; they don't get damaged. And out of 40 strain gauges, we only have 1 that didn't work. So it went really, really well. So we used load cells. So load cell at the support, loads, and there's a load cell at the support, and also there's a load cell for the actuator to record the load, string pots or string potentiometers to find the deflection. So that these are these deltas that we have over here for the deflected shape of the structure. And we use LVDT. So these are LVDTs, arrays of LVDT to check the displacement or relative displacement of concrete versus CLT. So we can see how much it's going to move and where we are on the composite action. And as I show or talked about, we have only 1 load over here. That's a shear diagram, and this the moment diagram. As you can see, it's all in negative moment. So that's the focus of this research. For the construction, we received the 5-ply CLT panels, a lot of them, from Mercer Mass Timber as donation. It was in May, I believe, 2023. So we used we cut them. We still have half of them for the next phase of these tests, basically. And then cut the rebars, move them to our structural lab and did the layout, making sure everything is good. Did the test setup. So my student Munder at that time, he did a really good job in going through the test setup, making sure everything is going to work. And then we put all the specimens because we wanted to make sure that for also pouring concrete, everything is ready. So we have the form around it, and also the interface layer between concrete and CLT. We want to have a waterproof layer that we receive also from rothablasts. So that's that green layer on top of the CLT. Then, as I mentioned, we add the strain gauges on the rebars to make sure that we can check when it's yielded, when it's at the maximum capacity or no, or so. And we have all the strain gauges when we have the maximum moment. So we have three, two at each side, one right in the middle, and then we have two over here, and then we have two over here. So we could check also the strain distribution over the length of the rebar as well. Then we put all these screws at 45 degree. Again, Munder did a very, very good job to make sure everything is exact. So we got really good result at the end, very similar and basically ready to put to pour concrete. So this is the CTC 196 screws with the jig that's at 45 degree. You can just put all of them. And then 8-inch on center double. That's the looking down to that TCC. And this is how you put things together. In the field, it's going to be a little bit different. So you may have a better way of putting things together. And then the rebar, so that's a transverse rebar, and then the other rebar will go on top of that, the longitudinal. At the end, what we have is all this ready for the for pouring concrete on top of the C or CLTs to make the timber concrete composite floors. So there's a concrete day. So we have 5 or 6 people at the same time, going through the pouring concrete. So we ask a local contractor come over here to WSU, and we had basically design of 4 KSI concrete. Pour concrete, make sure maybe vibrated the concrete, making sure that we have a really good engagement between the screws and the rebars, which is really, really important. And then we had a plastic on top of it, just making sure that for 28 days we have a really good curing for the concrete. So after 28 days we start testing. So for testing, as I mentioned, we put the CLT or at this point TCC, everything is cured. So concrete at the top, CLT at the bottom. That's the small specimen. That's a 20-inch wide specimen. This is a support because we will have an uplift over here. So we have to have an HSS on top of it, 2 load cell over here to check the load, and then actuator pushing down. And then this is the part that we will see maximum negative moment. And that's that's a point that we really would like to focus on. This is another slide that shows the instrumentation and how it works. These are the LVTs that I mentioned. We put it in this direction so they can get the displacement in from left to right and horizontal axis. And then in this case, if I have 2 very close, one in the concrete, one in the CLT, we can check the slippage. And we actually went through the slippage at the maximum moment and also at the tip of the cantilever beam. This is the test. In the middle of the test, we were pushing down, and then this is when basically we stopped the test at 14-inch or 14 or 15-inch displacement, and we saw a lot of ductility in the system. And ductility is really important because if you have a brittle system, then there is no way that you can distribute the load. But if the system is ductile, it holds that load. It does not have a fracture or failure. And in that case, you can distribute the load. The margin of collapse will go up, and then you can use or shed some of the load to other members and have a higher overall capacity for that floor system. So we got a very, very good ductility in the system. As you can see, we also track the cracks based on the load. So the numbers that you see over here this is the load number, not the actual load, tips of load applied. So that's a load number that we can go back to the testing log and see at load, for example, 27, what was the actual load inside of the inside of the actuator, and also what is the strain and like force in the load cells and all of those things. What is really, really important for these tests is we saw a compression failure in CLT. So that was the first time I saw compression failure in CLT, because as I mentioned, always CLT, because tension capacity is lower than the compression capacity of lumber. What you see always is tension at the bottom of CLT when you only test a flexural member, and then compression at top. Tension reaches its capacity and there's a tension and rupture, and we never can push it to have the compression failure at for CLT. But for the TCC, what we have is tension at the top, and there is a reinforcement over here. That's a rebar that takes care of the tension, basically. So it's expanding. You have cracks, but also you have crack inside of CLT because tension the top layer, but it's still holding because of the reinforcement and also the screws to transfer the shear to CLT. And in that case, we could push the CLT to have compression failure here. As you can see, there's a like buckling right over here and right over here too. So in other words, you can use the full capacity of CLT in this case and higher capacity plus a ductile system. That's another one. So that's TCC number 4, the last specimen. You saw exactly the same pattern as far as the cracks and also the compression. So it was yielding of rebar and then tensile failure at the top for CLT, but it didn't stop. And then we push it until we have a compression failure, and at that point, we reach the full capacity of the structure. So this is the force versus displacement. So that the vertical axis is the force that we applied at the tip of that cantilever. So that's this force over here. And then the displacement is the displacement at the tip as well. So we use this to be able to just monitor things, but you can do these plots for any other displacement. As you can see, we have a linear part. So everything was elastic until we got a little bit of cracking. And then now you see that there's a crack, but it's still holding, and you can like move and like push more. And there's another crack pushing more. At one point, it reaches the maximum capacity. And after that, there was like basically the compression failure. We could apply a little bit more, but we never could like go more than that. So in other words, now what you see is from when it start yielding and have that non-linear behavior, you can go from 6-inch at the tip to almost 15-inch, and that is the displacement capacity, or also like related to ductility of the system. If I put the CLT only, that's just a 2-point bending test that I showed in a few slides before. As you can see, the first or the second crack, there's a basically total failure. So the CLT is not ductile or doesn't have a good displacement capacity, but TCC does have that in negative moment. This is the force again, but that's the slippage between these two LVDTs. So this actually shows that we have like for a small load, there is no slippage, and then you have a little bit of slippage. And just note that these are in inches, so 0.02 inch, 0.04 inch. So at one point when we get to like very high capacity and maximum load, which was like 7,500 pound for that specimen, what we had was a lot of slippage between these two, and it means that the screw started to yield, and that's exactly the same thing that we wanted for the elasto-plastic capacity or the design methodology. We also could track the profile of that structure. So remember, I talked about like plane section remain plane and all of those. If it's a 100% composite action, yes, you can have a line, but if it's not 100% composite, you will see like a slippage between the layers. So these are the two LVDTs at the top. Then the two over here is these two over here, and then you have two right over here. So based on the displacement, we can see the profile of that system. and then basically track down and see like how much slippage we can get. So at one point there's like a slippage, and then it's going to like compensate that because now you have force on the other direction. But we could get the yielding of the screws for this design. So if I want to go through this very quick, this is like at 40% of the ultimate load. What we have is this. Then we have first rebar yielding, because we did the test for rebar, so we know when at what strain we have the first yield. This is when all the rebars yielded. So there was the first rebar, but you have like 10 of them. So when that is going to happen, so basically load distributed to all the rebars and they all yielded. Then at ultimate load, we have this, and then at large deflection, we've got like that part. So a lot of slippage over here between the two LVDTs. It means that at one point the screws are not are yielded, and they're not taking any more load. This is the rebar test that we did, and that's how we could backtrack and see like how the system worked. It's not just like checking the 60 KSI, because that's the nominal, but the actual yield was about like 70 KSI. So it's good to have those tests. This is the failure. If I want to like track those, that's a failure mode. That what we had first, like rebar yielding and rupture, and then this is the like rolling shear that we had, and then at the end we had the compression failure right over there. So based on the loads and the load numbers, we could go back and check and when compression failure happened, and it was basically right there. So that's the full capacity of the TCC. We did check the gamma method and the elasto-plastic. So as I mentioned, gamma method did not really work well for the negative moment. So this is the blue line, the bold blue line is the experimental, and the dashed green yellow is the one that's based on the gamma method and equation 1 and 2 that we showed like in the first couple of slides. And it seems that gamma method is overestimating the stiffness, so by 8%. So in other words, like gamma, if you use gamma method for this part of the structure, you're going to see you're going to expect less deflection, but you will see more deflection in actual design, which is not conservative. It's not safe. But when it comes to elasto-plastic method and the prediction based on the adjustment that we applied for negative moment, we could get to very close to the capacity from the experimental. So basically, we validated the elasto-plastic method for negative moment, and up to 96% of that. So basically, like 4 or 5% error, which is really good when it comes to experimental. That is the if there is any group effect, we did not see any group effect between small specimen and large specimen. So that 20-inch and then 40-inch wide. And then these are like the tests that we did for like other specimens. So I talked about the specimen number 1 and 2, but we did 4 of them. And as you can see, pushing over here, a lot of deflection is still holding, and that's basically a structural integrity. And this is exactly what we have for like reinforced concrete slabs. We wanted to have structural integrity, although it's yielded, but still holding that slab and distribute the load. That's the force displacement for like TCC number 3 that I'm gonna, for the sake of time, I'm gonna go a little bit faster on this one. Again, the same pattern that we saw, like compression at the bottom happened at the end. We have yielding of rebars, and then basically continuously it goes in to have a very ductile and also high displacement capacity. And this is when we add all of them together. So that's the force versus displacement or deflection at the tip. And as you can see, all of them did, and like all these specimens work really well. So the coefficient of variation, which is the standard deviation divided by the average, was about 3%. So 3% for an experimental test for COV is really good. It means that the specimens were like constructed really well and they behave really well, and it was basically a ductile behavior, because when you have a ductile behavior versus brittle, you have lower coefficient of variation, coefficient COV in this case, basically. That's the vibration test that we also did, the vibration test. This is something that we are still like working on for the TCC floor system. That's for only serviceability in this case. And then we did the FFT work to check what would be the frequency and how we can also work through the guideline for the serviceability and vibration for the continuous slabs. And then at the end, conclusion would be the first thing that we had was basically this is the first comprehensive study for CLT and like timber concrete composite with CLT for negative moment. It's for multi-span continuous, and it shows a very ductile system. We did the composite action and connector performance. We know that the shear for the connector is going to be the same. So in other words, the CTC 9160 screws, they don't care if it's a positive moment or a negative moment. It's all about the shear between concrete and CLT. So in that case, those tests can be used. But what was really important is the load path. So in the positive moment, concrete is going to be in compression, then transfer the load to screws, and then the screw is going to transfer the load to CLT. So that's a load path. But for negative moment, we have concrete in compression, then goes to rebar, basically. Then the rebar is going to be in tension. Like concrete is going to be like, in tension. It cannot take it. It goes to rebar. Rebar is going to see that tension, but then transfer that tension through the concrete between the rebar and the screws, and then the screws are going to transfer that to CLT. So that's a different load path, and we also verified that. So that load path is working really well. And in the TCC guideline, there should be a provision that shows what is going to be the maximum distance between the longitudinal rebar and the screws to be able to transfer that force. We concluded that the gamma method was kind of overestimated the stiffness for all the specimens between 10 to 15%. So it's unconservative for deflection or serviceability, but elasto-plastic method with some revisions, adjustment, and accurately predicted the experimental result and failure progression. Ductility was really important. We achieved really high ductility and structural integrity, as I mentioned, and it's really good to have something like that for a continuous span. If it was brittle, the marginal collapse will go down, and then also you have to have higher safety factors and all of those. But if you have a ductile system, it's going to be a lot easier to work with, and it support the structure and redistribute the force. And then the broader impact of this research is we developed a way of transferring negative moment with the TCC floor system. So it's not about only the floor system. So think of this: if you have a TCC floor in a high-rise building, 20, 30-story structure that has a concrete core or shear wall core, and you want to connect the diaphragm, which is the TCC floor, to the shear wall, and then also use the beam action in between and transfer some moment through the beam action basically to the columns that supported the other side of the floor. Then you have negative moment. You're going to develop negative moment at the connection between the shear wall and the TCC. And that negative moment is exactly the same as what we have over here. So again, this is good for the multi-span floor system, but it's also good for any negative moment that we would like to apply to a TCC. And with that, I would like to thank you. Thank you for your attention, and I'm open to address and answer any questions.
Awesome. It looks like I got a few questions here for you. So we'll just start from the bottom. So first one, it came about 20 minutes ago. Why did you test test with acoustic mat? Will there be much difference in test result between with and without the mat? Was the first question.
Very good question. So it's something that we also, I just want to mention that this is like phase one of these tests. So yeah, we have a mat in between, but there are some other ways of doing this. So what we wanted to do, we wanted to do a benchmark test of what has been done right now. And Rotoblas help us a lot to go through the construction of these TCC, the current construction. But it could be without mat or a spray, like waterproof spray, or something that we can apply to the top of the CLT or other kind of mat. What is important is for this test, we did not use any friction between concrete and CLT. So friction between them, we use basically zero for these tests, which is like good assumption.
Perfect. The next one was about 19 minutes ago. I assume your research was focused on linearly supported TCC slabs. What are the main issues that you would expect for point supported TCC slabs?
Well, this is for point supported, that's basically the columns that it's supported by a column or so. If we have that case, this is only for bending capacity, but there should be a punching shear. And so there's another failure that can happen in point supported slabs, and that's punching shear, the same as the concrete. So we definitely need to go through that design as well. And then also testing. And again, that's another phase of this project. And the one-way shear as well. So the short answer would be punching shear and one-way shear needs to be addressed for these slabs as well. Good question.
Cool. The next one was about 11 minutes ago. Were there any issues regarding moisture in CLT due to the concrete pouring and curing?
Great question. So not for these tests, because we had that interface layer that was a bituminous-based layer that was waterproof. So we did not see any issue when we look at the interface between the concrete and CLT. But that's something we need to address, and also the structural engineers and contractors, that if there is any crack in a building that's going to stay for, let's say, 75 years, 100 years, and there's a crack, how we can monitor the structure, making sure that, for example, that crack, opens up a little bit, structurally sound, as far as serviceability, that's good, but enough to get the water to the top of CLT. And then we have that waterproof layer. But if that waterproof layer fails, the water can get to top of the CLT, and then we will have decay on wood. And the top layer of wood is really important because that supports the screws. So that's something that we need to address on the inspection or the or monitoring these kind of structures. And again, the same as many other structures that needs monitoring.
Got it. The next question here is, what were the revisions and adjustments applied to the key method?
Good question. So the revision that we did, the first thing, you have to go back, and instead of, I think, sigma or tension capacity, it was tension capacity, you need to change it to compression capacity, because what we saw was basically the CLT failed in tension, but still we had capacity, and we can go higher capacity until the maximum capacity that happens when the CLT layer or the bottom lamination get to compression. So that was the first one. And it was another one that I don't recall exactly what that was about, like how we applied the like finding that neutral axis and applying the load or N times R in this case. So if you have two adjustment, then using elasto-plastic method, we could predict the capacity of CLT by about 5% error. So we're working on a publication for this. So as soon as I have that publication, those are basically all these technical aspect of this will be published very soon.
Perfect. I've got just a few more here. The next one is, did you observe or track any yielding/fracture on the screws transferring shear?
Yes, we did. So, like based on the LVDTs at the interface. So I don't know if I have. Yeah. So based on like checking these LVDTs over here, right over here, and then also the test that Rotherglas did, and that's the test I mentioned for only for screws. So we could go back, calculate, and see how much slippage we got. So that's basically the slippage. If I can go, yeah, so that is the slippage on some of the testing that we did. So I'm trying to see where we had those. So the slippage in the system, my computer is going a little bit crazy here. So let's see what I have. Yeah, okay, here. So this is slippage right over here. When you go and back calculate and see that from Rotherglas test that they did in their lab, this is and torch the entire thing. So we only have like 1/4 of these specimens still in our lab. We cut them, and then we could see like we could take some of the screws out, and then at the interface we could see the yielding of those. So one or two screws that we could retrieve, we could see the yielding of those as well. Any other question?
Oops, sorry, I didn't realize I muted myself. Yes, I got two more questions on one post and then a follow-up to one of the earlier questions. So first is a thank you for the presentation. They're wondering if you also carried out numerical simulations for the cases. If so, which material model did you use for concrete and plasticity, positive moment tests for TCC, and for timber? That's the first question.
So good question. So we did for this phase, we only, as I mentioned, we only did the benchmark test. So basically based on gamma method, based on elasto-plastic, we wanted to see if they are like working well. But no, we did not do a full high-end fine element analysis. In other words, like using abacus to do concrete, screws, and CLTs. That would be something that we are also like planning to do after going through phase 2 of this project. And that's basically the full nonlinear analysis. And then when we have analytical and then validation from experiment.
And then the next question is, what would you expect to observe in cyclic tests of GCC? Yeah, or TCC.
Yeah, for cyclic test, I mean, we did not did that for like cyclic testing. It's good, when it for the floor system, we don't see cyclic test. Basically, it's all like just monotonic loading, like pushing down. But then, as I mentioned, the broader impact of this is going to be something that we use the TCC connected to the shear wall in a high-rise building, and that can see positive and moment like a negative moment. And that's going to be another like set of testing, because in this case it's an unsymmetric structure. So you don't see like it's the positive negative stiffness, and also the capacity is going to be totally different. And then how we also connect it to that boundary condition. So is it like bearing to the shear wall? Is it like connected like as a positive connection? So that would be like a good question to answer. And that's, again, the continuation of this testing.
And then we'll finish it off here. So this is a follow-up to one of the earlier questions about the extensions to point supported PCC slabs. You mentioned punching shear and one-way shear testing, but are there any differences for biaxial bending from your perspective, having done the benchmark test?
Yes, if you have biaxial bending, these screws are only working on one direction. So in the longitudinal direction, the major direction of CLT, I would say, because if can you still see my screen? I think you can, right?
Yes.
So the screws are basically in this direction, and then like taking the shear in this direction. So screws, if you have like biaxial, then these screws are going to bend. They don't have that axial stiffness. So that would be something that you need either add other type of screws that can take bending in both directions, or like have resistance and strength in both directions, or put 45-degree perpendicular to this to transfer that shear for biaxial bending or two-way slab. That was a really good question.
Yeah, I think that's all the questions that we have for today. If anybody does have any questions, I know you shared on the last screen your email contact there. So please feel free to reach out. As we always say, whether it's an hour from now, a day from now, a week from now, a month from now, we're always here to answer your questions and continue the conversation forward. So again, thank you for the presentation, and we will see everybody on our next webinar.
Perfect. Thank you very much. Have a great day.